Good day, ladies and gentlemen. I, Yongwimon Lenberry, member of the Royal Society of Thailand and the director of the Center of Excellence in Mathematics, will be presenting our work on model analysis and simulation of impacts of COVID-19 pandemic on the economy, a case study of Thailand's GDP and its lockdown measures. As we all know, COVID-19 affects both the global and local economy. The extent to which the impact is felt depends a great deal on how governments and the public react to the disease. Here, a model is proposed to investigate the effect of the spread of coronavirus infection and the consequent measures taken in response to its spread to lessen its impacts on the society and the economy. The interaction between the number of infected individuals and the variations in the national growth product, or GDP, is modeled by a system of impulsive nonlinear difference equations with multiple delays. We are specifically interested in how different lockdown measures affect business recovery, as reflected by the national GDP. The model is analyzed to obtain valuable insights as to the factors that can yield different successes in the pandemic control and business recovery based on data of newly infected cases and cumulative cases weekly in Thailand. The model is simulated in a variety of scenarios to illustrate how different strategies and lockdown measures may give rise to different recovery rates. So the outline of my talk is as follows. First, a model system is proposed. Next, the analysis of the model is carried out. Then, the strategy by which the lockdown is relaxed in an incremental fashion is modeled. Consequently, numerical simulations of the models are presented in various scenarios of interest. Finally, a concluding remarks will be given. In order to model the impact of coronavirus pandemic on the economy and subsequent recovery, we let HN be the number in millions of healthy mobile individuals at week end who are able to interact with others and carry out transactions within the community. IN denotes the number of newly infected individuals in the community at week end. Equation 1 gives the number of mobile healthy individuals at week end plus 1 in terms of that at week end. This term is the rate of removal of healthy mobile individuals due to infection by the infected population IN, so that this term, as in the SIR model, is taken to be directly proportional to the product of H sub n minus 1 and I sub n minus 1, Ri being the removal rate constant of variation. We assume that an infected individual takes an average of 2 weeks before being detected, and hence the subscript n-1 on H and I in this term. The third term here represents the changes in the population due to natural causes, taken to directly vary as the population level at time n with variation constant C, where C is bigger than 0 and less than 1. EN denotes the indicator of business health, taken here to be the national GDP per capita at week end. Equation 2 gives the value of GDP per capita at time n+1 in terms of that at time n. This term is the rate of increase of GDP due to stimulation from interaction among mobile individuals, which includes the recovered individuals who take, on the average, 4 weeks to recover, and hence the subscript n-3 here. These two terms represent the rate of business loss, which decreases at the rate kappa BN/HN with the increase in the interaction between HN and BN. Equation 3 gives the number of infected individuals at time n+1 as a sum of that at time n, and the number of newly infected individuals R sub I, H sub n-1, I sub n-1, with the delay of 2 weeks. Equation 1 applies only in the weeks where n is not equal to kt, because this is the duration where there is no impositions of lockdown measures or their relaxations. If n is equal to 2k minus 1 times t, equation 4 then applies, at which instance the lockdown is lifted, with q sub uk being the fraction of h sub n that are allowed to interact socially with others in the community. If n is equal to 2k t, on the other hand, equation 4 will also apply, at which instance a lockdown is enforced, with q dk being the fraction of hn that are kept from interacting socially with others in the community. Thus, t is the length of the periods of lockdown and lockdown relaxation. Equations 2 and 3 apply only when n is not equal to 2k minus 1 t plus m plus d, during which time no business stimulus from inbound travelers is felt. At the times n, where n is 2k minus 1 t plus m plus d, the stimuli from inbound visitors or workers will kick in, as reflected by the GDP that jumps up by a fraction of beta BN, and infectious population feels weekly jumps of size nu from infected individuals from outside the country after a delay of D weeks. The parameters in the model system of equations 1 to 6 will be varied to simulate different lockdown and relaxation measures in various scenarios. But first, we carry out the analysis of the model system. Equating the right-hand sides to 0, we find two equilibrium solutions. The trivial steady-state solution, H0, B0, I0, a watch-out steady state at which all state variables vanish. Healthy as well as infected human become extinct, in which case no business can exist. The other equilibrium solution is the endemic one, HS, BS, IS, seen here, at which point healthy population becomes extinct while infection is endemic. Linearizing the model system about the washout steady state, we find the following Jacobian matrix, which has the following eigenvalues. Since C is bigger than 0, lambda 1 is bigger than 1, and therefore the washout steady state is unstable. The Jacobian about the endemic steady state is this matrix, having the following eigenvalues, so that the sizes of lambda 1, 2, and 3 are less than or equal to 1. The eigenvectors corresponding to the above 3 eigenvalues are these, where ms is this ratio and L is this ratio. From these eigenvectors, we form these matrices, which led us to the product of phi 1, phi 2, phi 3 to the power t minus d, and phi 4, whose eigenvalues determine the stability of the endemic steady state. In the case that Q sub k equals Q sub uk equals Q sub dk. This theorem states that for the model system of equations 1 to 6, the endemic steady state, HS, BS, IS, will be stable, but not asymptotically stable, provided that these two inequalities hold. If either inequality 7 or inequality 8 is violated, then the steady state will be unstable. Next, we adjusted the system of equations 1 to 6 to model the case in which relaxation of a lockdown is carried out incrementally. In other words, the businesses are allowed out of lockdown in a stepwise fashion. Noting that the system of equations 9 to 14 has the same steady states as equations 1 to 6, we can prove the following result in a similar manner to the non-incremental strategy. We can show that the endemic steady state HS, BS, IS of the model system 9 to 14 is stable, but not asymptotically stable, provided that T is less than or equal to T sub M, where T sub M is the minimum of these two quantities, and it will be unstable if T is bigger than T sub M. Next, we show some numerical simulations of our model using these parameter values, which have been estimated using online reported data on Thailand COVID-19 situation. In figure 1, lockdown is lifted in an abrupt manner, and the delay in business recovery, D, is 3 weeks. The simulation starts from the point where n is equal to 7 on this graph. In this scenario, business health becomes worse and worse. It is not able to bounce back to the original level. If a pandemic relief package of sufficiently big amount is injected into the industry by the government to help stimulate the business recovery so that it is reflected in the GDP increase within 1 week, the outcome is simulated in figure 2, where the lockdown is lifted in an abrupt manner and the delay D in business recovery is only 1 week. We see that business recovery is better and can reach the original level before COVID-19 within approximately 8 months. But the numbers of new cases are higher. To try to keep the new cases low, we tried a strategy in which the lockdown is lifted in an incremental fashion in this figure, in which we observe that the number of new cases each week is now lower, which could be more manageable. However, as expected, the economic recovery becomes less satisfactory. This is due to the fact that the mobile individuals become active in the interaction with each other in a gradual fashion. Social distancing may be keeping them apart or not get involved in certain risky transactions. Businesses then do not recover fast enough. In figure 4, the lockdown is lifted in an incremental manner, and the delay D is 1 week. The second lockdown lasts only 7 weeks. Here, we simulate a strategy that involves an incremental relaxation, but with a bigger jump at the week right after the lockdown ends, followed by smaller increments in a reasonable and realistic manner. We see that if we adopt this rule, as well as a shorter lockdown, the economic recovery is very promising, as seen in figure 4b, while the number of new cases does not peak at a very high level. In fact, the peak here is more or less the same as in figure 3a. Figure 5 compares the outcomes of strategies simulated in figure 3 and figure 4. The cumulative number of infected individuals resulting from the strategy proposed for figure 4 is higher than that for figure 3. Figure 6 shows a simulation of the modified model for the case that the lockdown is gradual, stretching 12 weeks instead of 9 weeks. Since the infection rate seen in figure 6a is not down to a low enough level, the lockdown process has to be kept longer before the number of new cases is in the single digits. This then hurts the economy more. It is clearly illustrated by our models that a sharp lockdown and a combination of sharp and incremental relaxation would yield more favorable outcomes, both in terms of economic recovery and control of the infection rate. A gradual lockdown brings the infection rate down more slowly. Also, the lockdown has to be kept up longer before the infection rate gets sufficiently low, which means the economy is hurt for a longer period. Thus, the models provide us with a qualitative projection of the outcomes of different strategies in lifting the lockdowns or mandating them, which can be very valuable for the decision makers in trying to navigate the difficult task of balancing between keeping the infection rate low and pushing for economic recovery. In making such decisions, qualitative projections are extremely important since they answer the questions of what if, also explaining the causes and effects of the outcomes better than a model that fits a set of data closely but does not describe the dynamic relationships. Thank you for your attention.